Okay, first I'd like to thank the organizers for the opportunity of presenting this work here. And I will be talking about, correlation measures and non-Markovianity. I'm from the Universidade Federal de Pernambuco, in Recife, and this was a joint work with Tony's group in ICFO. So the results that I will be presenting here is in this archive paper. But before I go really into the work, I would like to motivate a little bit what I think is interesting, the study of dynamics of open quantum systems. Oh, sorry. No, okay. So we know that if you think about physical systems in general, no physical system is really truly isolated. So this is a good approximation in many cases, but we'll be treating then the case where I cannot avoid to take in account the environment. So I have a system that I'm interested about the dynamics, and it's in contact with some environment, okay? And then I see three reasons why to study this dynamics is relevant. Well, first, because they are happening, and then as a fundamental point of view, it's interesting to understand why they are happening, what's the difference if I have different environments and things like this. But also we know that this unavoidable interaction between system and environment is causing the decoherence effects. So maybe if I understand better this interaction, I can make some engineering in the environment in order to minimize these decoherence effects. And also we have this non-Markovian dynamics, something that I will be talking here during this talk, and there are some effects which appear in some non-Markovian dynamics, which are this backflow of information. So the system is losing information to the environment, but it can be that at some point it recovers information, and then I can maybe explore this for quantum information processing. So I will be then describing the dynamics of the quantum system through the maps, which are linear operators that, okay, I want to guarantee that I'm taking density operators to density operators, so I would ask them to be completely positive and trace preserving. And to say if the dynamic is Markovian or non-Markovian, I will be inspired in the classical definition. So if I have a stochastic process where I have this random variable x that can take values xn and at times tn, I say that the dynamic is Markovian if the condition probability satisfies this condition here. Which means if I want to find out if the variable assume the value xn in time n, I just need to know what happens in time n-1. I don't need the whole story. So the Markovian dynamics will be like the future evolution just depends on the present state. And if I don't satisfy this condition here, then I really need the whole story to tell something about what will happen with this variable. Okay? So then we will define Markovian or Markovian in the same, like inspired by the same idea. But I will be looking to the maps. And I will say then that the map, dynamic is Markovian if the map is divisible into other maps, like one that is taking the state from 0 to time s, and then from time s to time t plus s, which means that if I know the state in time s, then I can say what will be the state in time t plus s. I don't need to know what was the state in time 0. So again, the same idea that the future evolution just depends on the present state. But if I don't satisfy the divisibility property, then I say that my dynamics is non-Markovian. So I really need to know what was the state in time 0 to tell something what will be the state in time t plus s. And then as I said, in some cases, these non-Markovian dynamics will imply a non-monotonic decay of information. So this can appear in different quantities. And okay, just to give two examples, what are the most typical quantities where I can see this backflow of information. One is distinguishability. So I can think about, okay, I start with some state and evolve it. And I start with the orthogonal state, so they are completely distinguishable. Okay, I'm thinking about qubits Bloch sphere, okay? They are completely distinguishable, and then with time, they get less distinguishable, but it can happen if I have a non-Markovian dynamics that they will start to get distinguishable again. So this will be a sign of non-Markovianity, okay? And I can also look to the entanglement between the system and an ancilla, and I also can start with some, okay, they are maximally entangled, and then with time, if I have a Markovian dynamics, the entanglement will necessarily decay monotonically. But if I see that the entanglement has increased at some point, then this will also a trace of non-Markovianity. But it doesn't mean that all non-Markovian dynamics will present this backflow, okay? Some non-Markovian dynamics will, but not all of them. So then when I started to work with open quantum systems dynamics, I questioned myself, well, is there any quantity that will always identify a non-Markovian dynamics? And I had this question in mind when I saw this result here from Francesco Buscema and Nilanjan Nadata, where they show, yes, there is an equivalence between divisibility and a monotonic decrease of information, okay, in classical and in quantum stochastic processes. And what they are doing, okay, just what concerns us, they are exploring this theorem where I have that a quantum solution is Markovian if and only if the trace norm of any emission operator is decreasing, which means that if I have a non-Markovian dynamics, I have to be able to find at least one emission operator where this trace norm is not decreasing, okay? And also can see that any emission operator can be written in this way. Okay, P is just a number that is changing from 0 to 1, and here rho 1 and rho 2 are density operators. So I can relate this result to another problem, which is what happens if I have an ensemble of states, and with only one measurement, I want to guess what is the state. And I see then that the average probability to correctly identify the state, in this case already the optimum average probability, is related to the trace norm of a emission operator, which is constructed by these two states from this ensemble. So then they are showing that this guessing probability has to increase at some point if I have a non-Markovian dynamics. But the problem is that, okay, as I said, I have an ensemble of state and I will have to make some measurement, and it's not trivial, I don't have a recipe how to construct this ensemble of state, depending on my dynamics, and what will be the optimized, like the best measurement to give me this optimum guessing probability. So, okay, it's good that we know we have some quantity that we will always identify, but sometimes, okay, it's not straightforward if we will be able to find this ensemble of states or not. And another thing that, okay, I still had in my mind is okay, this is the guessing probability, but thinking about really exploring non-Markovian dynamics to some quantum information processing, and consider that we are always talking about entanglement or some type of correlation, I was asking myself, okay, is there a correlation measure capable of always detecting a non-Markovian dynamics? And, oh, yes, but, okay, it's also not a very trivial correlation measure, but anyway, we were searching for a quantity that could satisfy these three conditions here. So we defined our quantity as a correlation measure if it satisfies these conditions. And the first one, it has to be bigger. Okay, I'm just saying that we thought these are the three properties that we thought, okay, this it's reasonable that this quantity satisfies these three conditions. So it's bigger than 0, and it has to be 0 if I have a product state, so which means that I'm considering that I can look to correlation measure that maybe just classical correlation will be enough to identify this non-Markovian dynamics. And it has to be non-increasing under local operations. So it doesn't make sense that with local operations, I will create some correlation, okay? Well, and then we were looking to the correlation measures that we have already and to see, okay, maybe they are already doing the work and we don't know. Of course, we knew that, like, we had the feeling that they are not doing the work, but of course you have to show at least one example where you have this failing, and then you can say, now it's, okay, now I can really look for another measure because the measures that I have, they are not doing the work. So we have then, first we look to entanglement, Again, I'm looking to like a system and an ancilla, the entanglement between these two guys. And I can think about, imagine you have this entanglement breaking channel from time 0 to S. I can start with a state with some entanglement, and then what I will have, okay, it will take me to a state without entanglement. And afterwards, I apply a positive map, which will not be able to create entanglement. So in this case, and I'm just giving an example, okay? But I have to choose this positive map in a way that the total map is still CPTP, okay? Since the second map, the map from S to T is a positive, I'm looking for a non-Markovian dynamics here, okay? So then I'm just telling you an example where necessarily I won't see the recover of entanglement and I have a non-Markovian dynamics. Okay, entanglement won't do the job. So how about mutual information? We had some numerical evidence, like I had some examples of dynamics where I was searching and searching for different states, also consider system and ancilla, and I couldn't find any recovery of mutual information. But we weren't completely happy about it because someone could argue, okay, maybe the space of the states that give this recovery of mutual information is so small and you're not searching it properly, and that's why maybe you cannot see. Okay, and then we came out with some analytical example, which is very non-trivial, so I don't want to go into details, but this is an informative part of the talk. I'm just telling you that mutual information will also fail. So we have some examples where it won't work. And then we were thinking, well, okay, maybe we have to come out with a new idea and define a correlation measure so that I guarantee that I can always witness non-Markovianity. And for this, we were exploring Francesco's papers, like we need two elements from there. One are these maximally entropic POVMs. So I start with a state, a bipartite state, rho AB, and I will perform some measurement on part A in order to prepare the states on part B. So I'm doing some measurement, which can be any element of this POVM. And I have here in my example n outcomes, and for each outcome, I have prepared B in a different state. They don't necessarily have to be different, but okay, I have n possibilities here. And in this way, okay, I'm preparing then this ensemble with n different possibilities for B with probability pi, okay? And I say that the POVM is maximally entropic if the probability of this, the preparation of these B states, if they are equal, okay? If I have here the pi is equal for any I state. Another thing that I will explore is also this guessing probability, as I already told you. So I'm defining it, so given an ensemble of states, the guessing probability is the average probability to correctly identify a state from this ensemble, maximizing over all possible measures. Okay, so the guessing probability I'm defining already as the optimum probability, average probability to correctly identify the states from this ensemble. And as I said, if I'm just looking to an ensemble of two states with equal probability to occur, the guessing probability will be related to the distinguishability or to the trace norm of these two, difference of these two states. Which means that if my ensemble just have rho 1 equals to rho 2, my guessing probability will be 1/2. So I cannot really, there isn't any measurement that I will be able to tell you, oh, this was state 1 or not, this was state 2. And then I will just randomly say 1, 2, and then this will give me a guessing probability of 1/2. And then we came with this correlation measurement, which looks kind of strange. But I will try to convince you that this quantity satisfies the three properties that I told you at the beginning that I wanted. Okay, if I'm saying that I have a quantity that is a correlation measure, it has to satisfy these three properties. So this correlation is then defined by the most distinguishable ensemble of equiprobable states of either system A or B. So I wanted some symmetry. I didn't want to have like ancilla. I want really correlation between two things that are equally important, let's say like this, that can be obtained by performing measurements on the other system, okay? Always I have this game that I have two parties, and I will use one party to prepare the ensemble of the other party. Okay. Then I need to show you that it satisfies these three properties. Let's just start with this one, where I show, okay, this correlation measure is always 0 if I have a product state. If I have a product state, and I'm just taking the case where I'm doing the measurement on part A. And then what happens is that I'm preparing all the part B in the same state always, okay? Doesn't matter what I do here, I will always have row B in the same state. And since I'm just looking to maximum entropic POVMs, I'm already imposing that the probability is equal to have all these states, okay? I fixed this family of POVMs. Which means that if I look to the guessing probability, as I said, if I cannot distinguish the states, the best that I can do is say, wow, it was 1 or 2 or n, and then the probability of guessing will be 1 over n. But since I'm maximizing this probability of it correctly identifying, the best thing that I can do is say, well, let's keep it just to two POVM elements, and then I have just two possibilities, or two row B, and then my guess will be 1/2. And then if I go back there, here. So I have this 1/2 minus 1/2, and then I have 0. And that's why maybe you ask yourselves, why does she have this 1/2? So it's just to guarantee that I have the 0 when I have a product state, okay? And then also, this is the minimum probability, in fact. So the guessing probability will be higher than this, which means, okay, I guarantee also that it's bigger than 0. So the worst case scenario is this one, when I have my ensemble with all equal states, when I cannot distinguish them in any way. And also I have to show, okay, that this quantities is not increasing under local operations. And I would just try to convince you, looking also just fixing one part. So I'm looking to the correlation when I'm measuring the A part, and when I'm applying a map that's only the A part, okay? I'm applying the local operations only in the A part. So my evolved state will be given by something like this. Here I'm already using the Krauss representation of this map. And if I look then now to the states that they are generated after I'm doing the measurement on A, I can see, okay, here I had the evolved state. I would call this as like the evolved ensemble state. So these are the elements of this evolved ensemble state. I can write it, okay, I can write it as I have the evolved state applied and the element of POVM applied to this state. But I can also think about it as the initial state with some kind of different element of POVM, which is this guy here. So it's the same, here they are in the same Krauss operators, but applied now to the element of the POVM, which is kind of evolving the elements of the POVM instead of evolving the state. And then what I see, the ensemble that I'm generating now, I don't necessarily have to say, I don't have to stick to the evolved state, but I can just keep the same initial state, but now I'm looking to a different family of POVMs. So if now I'm looking to the correlation measure that I have defined, this is the correlation measure at the beginning, before I apply the map. And this is the correlation afterwards, okay? In principle, this guy should be here, but I already convinced you that it's the same as having the same initial state and a different family, a different set of, a different POVM, sorry. So what I see here, I'm doing this maximization in order to maximize this PGS. So I will find then a POVM that will maximize this PGS. And here, this imagine that, okay, I found this group. What happens here is that the best thing that I can do is to find the same POVM. I won't be able to find another POVM to give me a better p-guess. Because if I find something like this, that means that the work that I did here before, it was wrong. No? So, which means that this quantity can only be equal to this or smaller. It cannot be bigger. And then I'm proving to you, okay, if I'm applying a local operation, just thinking about part A, this correlation measure can only decrease. And of course, I have to do the same job for part B, but I won't do it, okay? I just wanted to give you a little bit of the flavor. But it won't increase. So anyway, well, but I'm telling you all this. Okay, we have this correlation measure and this quantity, that's a correlation measure. But okay, but how do you show me that this will witness non-Markovian always? Because this was my task, to find a correlation measure that always witness non-Markovianity. And then we use another result from this paper here, also like Bogdan and Max, which are together with us, and Tony, where they find if they have a non-Markovian dynamics that is bijective, which means that this dynamic has to have an inverse, which is not necessarily true for all dynamics, okay? So we have some constraint here. They show that if you have a non-Markovian and bijective dynamics, it's always possible to find a pair of states where this distinguishability will decrease, okay? And they show how to construct these states. So it's not, okay, this is something we knew, okay, there should be some states that the distinguishability will decrease, but they show how to construct these states. And this is what we were exploring also in this correlation measure. So now I had part A and part B, but I will add an extra ancilla. So my part B will be system plus this A prime system. And I will choose then to write this state in this form here, which means that, okay, here the part A will be kind of a flag state. So if I have A in 0, then A prime S will be in the states row. If I have A in 1, A prime S will be in state row prime. And I will choose then my elements of POVM in this form here, in a way that I will be preparing the state Sn and prime as this state. So row 1 will be the convex sum of row and row prime, and also row 2 will have this form here. Which means then if I do the calculation, and I look to the correlation, here I'm just showing you the CA, but okay, we could also do the same for CB, okay? I think it's tedious to do just the two things. I hope you are convincing when I just do this for CA. So I'm looking to the maximization of this PEGAS, but remember, if I just have two states, the PEGAS, the optimum PEGAS, was related to the distinguishability. So this is exactly what's appearing here. And what they showed is, okay, they know how to construct these states in order to always see an increase in this trace norm if I have a non-Markovian dynamics. And so if I can show that this quantity is always, okay, I can find at least one pair of states that I will see this increase, then I will also see an increase in the correlation. Okay, so we are exploring the same result. So with this, I have showed you, okay, we have a correlation measure. We are proposing a new correlation measure. It's kind of, it's strange, I would say, maybe. But it satisfies all these properties, and I can really construct states in order to see this backflow of information in terms of this correlation measure, and this will be true for all non-Markovian dynamics. Well, I already said my summary, but and also the way that I can find these states, I can do it through, this is important to say, I haven't written here, I can do it through SDP. So I can construct these states, and I can I can do it effectively, okay? Well, I think there are many open questions still in this work, but for me, what's like the most important thing, how can I use this kind of backflow that I will be identifying by this correlation measure? Is there any protocol that will benefit from this backflow? I don't know, okay? I still don't have this answer. I hope, well, I don't know. This is something, and yeah, I think that's all. Thank you for your attention.